Hello everybody, my name is David Cruz. I am a PhD student in the program of Forest Biomaterials at North Carolina State University. For me, it is of great pleasure to be here today, sharing with you some preliminary results for the Paper Sludge to Fuel project, PStF. This project is a collaborative initiative between NCSU and the National Renewable Energy Laboratory. This project is funded by the U.S. Department of Energy through its Bioenergy Technologies Office. As we all know, due to the increasing global demand of energy caused by the growing world population and the reduction of oil reserves, researchers around the world have focused their effort to investigate and propose alternative sources for the production of energy. Within this project, we are proposing a catalytic pathway to produce a hydrocarbon product that can be blended with jet or diesel fuel, using as feedstock the lignocellulosic biomass contained in a solid waste stream from the pulp and paper industry. In industry, landfilling is the most common way to dispose paper sludge. This not only represents a negative environmental impact in terms of land use, but also an important cost for companies. It is estimated that in the United States around $240 million are paid every year to dispose this material. Paper sludge contains a large amount of wood fibers and fines, representing a good source of carbohydrates. In this study, we have found a carbohydrates content of about 53% of total dry solids, having glucan, also said cellulose, as its major constituent. The final goal of the PStF project is to produce a hydrocarbon product in the C15 range. By the other hand, the main goal of the milestone of the project discussed today is the development of a model that allows us to understand how the different parameters associated to fixed and variable costs and also to financial factors contribute to the minimum fuel selling price of the final product. The first step in the proposed chemical transformation pathway is not displayed in this slide, and basically accounts for the enzymatic hydrolysis of the biopolymers cellulose and xylane, using 10.4 milligrams of enzyme per gram of cellulose at 50 Celsius degrees to produce the liberation of the monomeric sugars. The glucose and xylose then are dehydrated on aluminum chloride at 195 Celsius degrees, resulting in the formation of the corresponding furans. 5-hydroxymethyl furfural and furfural are then cooled down to 40 Celsius degrees in order to enter to the aldol condensation reactor. Here, the furans get in contact with methylethyl ketone and the liquid catalyst sodium hydroxide to form the corresponding monoadducts before finally condensing into the B-adduct as shown in the graph. The last step consists in the hydrodeoxygenation reaction of the B-adducts to hydrocarbons on a solid catalyst at 300 Celsius degrees. In this slide, we have the basic flow diagram for all of the chemical processes and unit operations required for our theoretical process plant. We have divided the plant into 7 functional unit areas. In this slide, you can appreciate only the pieces of equipment in areas 100 to 400 used to estimate the total direct cost of the plant. In the base case, 750 metric tons of dry sludge per day enter the system to be processed. In area 100, the wet paper sludge is received and stored. In area 200, the sludge is diluted using water and an adequate system to remove 99.9% of ash. According to our experimental results, around 70% of fibers are retained in the system. In this same area, the fibers are acidified by using hydrochloric acid and then stored. In area 300, the acidified fibers are mixed with the enzyme and then sent to the enzymatic hydrolysis reaction system. After 96 hours, the remaining solids present in the hydrolysate are removed to be incinerated. In area 400, the solvent dioxane is added to the clarified hydrolysate at a ratio of 2:1 in order to stabilize and protect the 5-HMF and the furfural. Then, the furan stream is mixed with aluminum chloride before entering the dehydration reactor. The furan products from the dehydration reactor are combined with sodium hydroxide and methylethyl ketone before entering the aldehyde reaction system. The product mixture of the aldehyde condensation reaction contains dioxane that should be recycled. So the isotropic mixture leaving the top of the distillation column is recirculated back. The heavy mixture containing the processed B adduct is sent to the decanter to remove the water, and the light stream is processed in the hydrodeoxygenation facility, where hydrogen is added to remove the oxygen present in the B adduct products. The produced water is removed and the final hydrocarbon product can be stored. Areas 500, 600, and 700 account for the wastewater treatment, the heat and power, and the utilities plants. In this diagram, we can see how information flows in order to determine the minimum fuel selling price and its sensitivity analysis. Experimental data obtained by NCSU and NREL and the information for existing technology were used to develop a process model using Aspen Plus version 11. The corresponding rigorous mass and energy balance was obtained. A mass balance was developed in Microsoft Excel using the results from the rigorous model in Aspen Plus. Additional attention was required in order to validate that the balance around the distillation column was in accordance with the Aspen model results, which are in fact taking into account the isotropic nature of the dioxane water mixture. One of the biggest challenges that we experienced during the determination of the minimum fuel selling price for our expected product and its corresponding sensitivity analysis using a software such as Microsoft Excel was the required interconnection between the two used software solutions. To overcome this situation, especially for the energy balance, we run the rigorous model in Aspen Plus after modifying different process variables, and we obtain functions to describe the response of the output variables to an inlet variable modification. Those correlations were obtained at the expected ranges for the sensitivity analysis modifications, so this analysis could be performed using the Microsoft Excel model without requiring an additional modification in the rigorous Aspen model. Additional input information was needed to be fed into the main Microsoft Excel model. To ensure consistency between these and other biorefinery projects funded by DOE, different NREL reports were used to estimate the total power consumption of the plant, as well as the equipment cost and the catalyst and other chemicals cost. Information for diesel fuel was obtained from the U.S. Energy Information Administration. This information and the main Microsoft Excel model were used to determine the operational expenditure and the capital expenditure. Economic parameters used in previous NREL reports were also used in our model to determine the discounted cash flow, including an internal rate of return of 10%, equity of 40%, an income tax rate of 21%, a project contingency of 30% of total direct cost, and a loan rate of 8% for a 10-year term. After defining realistic variation for 56 process variables and using the OPEX, the CAPEX, and the calculation for the discounted cash flow, the minimum fuel selling price for our expected product in this base case, as well as its sensitivity analysis were obtained. Here we have a summarized version of our preliminary results. Within this base case model, we have found a minimum fuel selling price of $5.97 for each gasoline gallon equivalent in 2020's US dollars. The model is estimated an annual total production of 14.2 million of GGEs, which when comparing to data from the US Energy Information Administration would represent almost 1.94% of the total diesel consumed in the USA during 2019. In the manufacturing cost table, we have the complete breakdown of the minimum fuel selling price for 1 GGE, including all the factors contributing to the final result: operational cost, credits, fixed operating costs, capital depreciation, average income tax, and average return of investment. It is evident that the top three operational parameters impacting the minimum fuel selling price are the cost of the ketone, the cost of the hydrogen, and the cost of the solvent use. In this same table, we have two additional lines including negative values representing credits. The first one due to the sludge disposal, and the second one due to the electricity surplus found in the model, accounting for about 31% of the total 7.4 megawatts of power generated in the plant. In the right upper corner of this slide, we have the results for the sensitivity analysis for the 10 most relevant variables impacting the minimum fuel selling price. We found the dioxane to water ratio to be the most relevant variable. These results indicate that if we could obtain the same dehydration reaction performance when using a ratio of 1 instead of a ratio of 2 as in the base case, we could obtain a minimum fuel selling price of $4.76. The following variables in importance according to our sensitivity analysis results are the fiber consistency for hydrolysis, the loss of solvent, and the plant scale. If at least those 4 variables could be moved to the optimistic values, the minimum fuel selling price could be reduced down to $4.58. After these results, the teams have agreed to work on the following 4 activities. First, to study and evaluate different chemical pathways to produce the methylethyl ketone from a renewable source and integrate the most viable alternative as part of the current process plant to evaluate the effect of this potential reduction in cost on the minimum fuel selling price of the expected product. Second, to optimize the dioxane to water ratio for the dehydration reaction and study the recyclability of this solvent in the system, and also to propose and validate at lab scale alternative mechanisms to recycle back this solvent, which would also cause the modification of the current layout of the plant. And third, to work in the lab to optimize the hydrolysis reaction using the highest possible consistency of fibers. It is important to mention that in this study, we are not considering carbon or any other additional credit. As for the conclusion, a full plant model was developed to determine the minimum fuel selling price and its sensitivity analysis for the liquid fuel product from paper sludge. Also, the preliminary determined minimum fuel selling price is comparatively higher than values reported by NREL in previous reports, mainly because of 2 reasons. The first is that NREL considers a much larger capacity plant. And second, because in those reports, NREL considers the production of co-products that bring fuel costs down. Therefore, in my opinion, $5.97 per GGE at this point of the project is not a bad number. Finally, the most important conclusion today is that the developed model is now serving as a tool to guide our work in the lab, by pointing out those process variables which we should focus on in order to potentiate the results by reducing the minimum fuel selling price. So this catalytic pathway can be validated as an economically viable alternative for the production of a hydrocarbon product from lignocellulosic biomass in paper sludge that can be blended with jet or diesel fuel, at least in a proportion of 50%. We want to thank to all the people attending this virtual presentation today, and we also gratefully acknowledge the support for this research to the Department of Energy of the United States. Now, I will be happy to answer your questions if you have any. Thank you so much.